Hey guys, welcome to video 71. We're going to continue our analysis of amplifiers that are out there in the world, and today we're going to look at the Marshall SLP 100 Super Lead Preamp. This is also sometimes called the Plexi, and it's a very iconic amplifier used by a lot of guitarists over the years. Jimmy Page, Jimi Hendrix, Eric Clapton, Eric Johnson, and a bunch of others. And it actually comes in two different flavors, the original 100-watt version and a 50-watt version as well. The preamp section is identical in both. There's a slight difference in power supply voltages, but it's not that significant. All right, so let's start here by just going through an overall view of what's going on with this circuit. Starting here on the input side of the amplifier, we've got two different preamps. Inputs 1 is a lower gain preamp than inputs 2. Both of these preamps have two input jacks, a low gain input and a high gain input. And these input networks are identical for both amplifiers. If we use the high gain input, we don't get any attenuation. If we use the low gain input, we get a voltage divider formed with these two 68k ohm resistors that gives us a division by 2, so it cuts the gain of each amplifier in half if we use the low gain input. In addition to forming attenuators for the low gain inputs, the 68k ohm resistors also serve as grid stoppers. And if you remember from the last video, grid stoppers are used to reduce the high frequency gain of these amplifiers so they don't pick up extraneous radio frequency noise and so on. And it also tends to reduce the tendency for oscillation of these amplifiers as well. Stage 3 of the amplifier serves as a buffer between the two input amplifiers and the tone stack, which is a relatively low impedance section of the amplifier. That's why V2B is a cathode follower. It's got relatively low output impedance, so it can drive the tone stack effectively. I may or may not get to the analysis of this stage in this video. It depends how long it takes to get through these ones. If I don't do it in this video, I'll make a separate video analyzing stage 3, and we'll do that next. But finally, we've got this filter/decoupling network, and all this does is provide some additional power supply filtering to make sure that we don't have any supply ripple present on these rails. Class A single-ended amplifiers like this are very sensitive to power supply ripple, and this just ensures that we have a really clean supply rail here. And it does decouple the two amplifiers. That is, it isolates stage 3 from stages 1 and 2. These are relatively large filter capacitors, so we're pretty well assured of having a very, very clean supply rail here. And the voltages I have listed, I took from sources on the internet. I'm assuming this 260 volts is accurate, and I think it applies to the 50-watt version of this, but it really doesn't make that much difference. And we'll see how accurate this 250 volt number is after we determine the IPQ values for V1A and V1B. Now let's go on over and we'll start the analysis of inputs 1. Here is the inputs 1 section of the amplifier and the plate curves for the 12AX7. So let's start by plotting our DC load line. We know that VPK cutoff is going to be VPP 250 volts, and IP sat, the plate saturation current, is going to be VPP over RP plus RK, but since RP is so large, I'll just neglect RK for right now, and we'll approximate it as VPP over RP, and that's 250 volts divided by 100 k ohms, and IP sat is 2.5 milliamps. So let's find these points and draw a straight line between them. Here is 2.5 mils, 250 volts, and here is our DC load line. Next, we're going to locate the Q point by plotting our bias line. Let me center this up a little bit better. And there we go. So what we're going to do is make this little table where we're going to choose VGK and find the resulting IPQ. And again, I'll start with 0 volts, which gives us 0 plate current. That's the origin of the graph. And let's see if I choose a convenient curve. Let's say we'll try VGK of negative 2.5 volts. That's this curve over here. So VGK is negative 2.5 volts. That gives us 0.93 milliamps of plate current. So let's find that second point, which is right over here. And let's connect these up. We'll use a green line this time again. And here is our bias line. And let's locate our Q point. I'm going to do that in purple again. It's right here. And it looks like our VPK Q value is about 185 volts. And our IPQ value, if we come across here, I'd say that's about 0.65 milliamps. Next, let's get ready to do our small signal and large signal analysis. So let me clean off the workspace a little bit here. And we'll begin by determining our effective load resistance on the plate of this tube, and that's going to be RP in parallel with this mess out here. We'll assume that the pot is set for maximum output, so that's going to give us 1 meg in parallel with these two in series, which are pretty close to 1 meg. So let's say it's going to be 1 meg in parallel with 1 meg, 500 k ohms. All right, so our R prime L for this circuit is going to be 100k in parallel with 500k approximately, and that works out to be about 83 k ohms. Now let's determine the small signal plate resistance R prime P, which is going to be R prime L in parallel with little rp, and we're going to use little rp of 70 k ohms here. I got that from the data sheet using the average characteristics based on our plate current, and working through this I came up with these values for our parameters. So what we've got here is 83k in parallel with 70k, and that's approximately 38 k ohms. Next, we want to determine our effective R prime K, that is the AC equivalent cathode resistance. And we saw this situation back in video 69 when we analyzed the JCM 800 master volume preamp. This 0.68 microfarad cap does not make a very good bypass here. So at 200 hertz, it looks like about 1200 ohms. So we're going to estimate R prime K as about 1 k ohm on average and just go with that. And now that we've got all these AC equivalent resistor values out of the way, let's go ahead and determine our voltage gain. AV equals negative GM times R prime P over 1 plus GM times R prime K. And that is, let's see, negative 1.4 millimos times 38 k ohms divided by 1 plus 1.4 millimos times 1 k ohm. This works out to be about negative 53 divided by 2.4 for a gain of negative 22. And remember, if we're using the low gain input, we're going to cut this in half, so we'd have a gain of -11 in that case. Now let's clean up our workspace a bit, and we're going to determine our AC load line. We don't need R prime P. I'll keep R prime L up there so I don't forget what it is. And because R prime L is so large compared to R prime K, I don't really need to factor R prime K in. It will have some effect on the AC load line, but very little. So now let's go ahead and do those calculations. IP sat is IPQ plus VPKQ divided by R prime L. So we've got 0.65 milliamps plus 185 volts divided by 83 k ohms, 0.65 milliamps plus 2.2 mils for an IP sat of about 2.9 milliamps. VPK cutoff is VPK Q plus IPQ times R prime L. So we've got 185 volts plus 0.65 milliamps times 83 k ohms, so 185 volts plus 54 volts, and that comes out to be about 239 volts. Let's change our pen to red. We'll locate these points. 2.9 mils is right about here, and 239 volts is here. And now let's connect these up. And here is our AC load line. And rather than try and squeeze in all the labels and stuff over here, I'm going to go on over to the next page and give you the consolidated version of all this information. And here you go. And I also threw in the values for VO max and VO min, the maximum output signal swing. VO max, of course, is the distance from the Q point, VPKQ to VPK cutoff on the AC load line, and it's also this term in the VPK cut equation. VO min is the maximum negative output voltage swing before we have the Q point cross the VG equals 0 volt curve here. And if we do cross that line, remember we can get significant grid current flowing, which we don't want. But this is not a hard clipping point, unlike VPK cut, which is a pretty hard clipping point. And anyway, I threw that in there, and let's go on over and take a look now at the inputs to section. Here's the second input section, very similar to the first. We've got the same supply voltage, the same plate resistor, the same input Jackson attenuator section, and the output is roughly the same, at least from the perspective of the vacuum tube, although we are feeding into the next section from this voltage divider, so it's going to divide the gain of this amplifier by 2 in the end, but we're not going to worry about that here. We're just going to do the analysis on this stage as it is. And the main difference here is the value of the cathode resistor. We've gone from 2.7K down to 820 ohms, and that's going to have a significant effect on our Q point location. Okay, so let's start with our DC load line, and it's going to be identical to the previous stage because VPK cutoff is again VPP, which is 250 volts. IP sat is VPP over RP plus RK. But again, R sub k is small enough to ignore, so we're just going to say it's approximately VPP over RP. So that's 250 volts divided by 100 k ohms, which is 2.5 milliamps. So here's our DC load line. And now let's find our Q point. So again, I'll just set up that little table where we'll choose a convenient VGK, find the resulting I sub P, and we'll plot the bias line based on these points. I'll start with 0, 0 again, which is always a nice, easy choice. And this time, let's say we're going to choose the negative 2 volt VGK curve here. So if we have negative 2 volts, that gives us a plate current of about 2.4 milliamps. Okay, so our first point is here. Our second point is the 2 volt curve at 2.4 milliamps. That's right here. And let's again change our color to green and draw our biasing line, which is right here. And let me switch colors here to purple, and I'll draw in my Q point. And its coordinates are, let's see, we're coming down. That looks like about, oh boy, 145 volts, I'd say, 145 volts. And our current is about 1.1 milliamps. All right, now based on this Q point location, I used the data sheet to determine the small signal parameters for this half of the 12AX7. So it's 1.6 millimos for GM, and little RP is about 60 k ohms. Now let's go ahead and calculate our AC equivalent resistances. I'll change my color back to blue, and let's start with R prime L, the large signal load resistance in the AC equivalent. That's going to be R4 in parallel with this mess, which is roughly the same resistance we had previously. This works out to be about 500K. So we've got 100K in parallel with 500K, and that's about 83 k ohms. Now R prime P, our small signal AC resistance, is R prime L in parallel with little rp, so this time we've got 83k in parallel with 60k, which works out to be about 35 k ohms. Now our cathode is fully bypassed this time. 250 microfarads is a really good bypass, so R prime K equals 0, and our voltage gain is then AV equals negative GM times R prime P. So negative 1.6 millimos times 35 k ohms gives us a voltage gain for the tube of about negative 56. Now remember, that gain is being effectively cut in half by this divider, but we do have a much higher gain for this half of the triode than we did for the input 1 section. And we'll wrap up the analysis of this section by finding the endpoints for the AC load line. So we've got IP SAT, which is IPQ plus VPKQ divided by R prime L. So 1.1 milliamps plus 145 volts divided by, where are we, 83 k ohms. So it's 1.1 milliamps plus, this works out to be about 1.7 milliamps for an IP SAT of about 2.8 milliamps. Then our VPK cutoff, and I'm running out of room here, but I'll squeeze it in, is VPKQ plus IPQ times R prime L, 145 volts plus 1.1 mils times 83 k ohms, and that's going to work out to be about 236 volts. So here are the limits for our AC load line, and let's sketch that in now. So I'll change my color to red, turn on the line drawing tool, and we're going from 2.8 milliamps right here to 236 volts, which is right here, and there is our AC load line. Now I'm going to go over to the next page and give you a version of this that's nice and neat as usual. And I've also calculated the clipping points as well, so here you go. And again, I know I flew through the analysis of this second stage pretty quickly, but it was very similar to the first stage, so I don't think that should be a problem. And let's go on over and consolidate all the information we've gathered so far. All right, here's our schematic. We started with section 1. The gain was -22. We had a Q point of 0.65 milliamps plate current, 185 volts VPK, and our cathode voltage is about 1.8 volts. The second section had a higher gain. It was about -56, operating at a higher plate current, 1.1 milliamps, 140 volts, and its cathode voltage would be about 0.9 volts. All right, now I'm not going to do stage 3 in this video. I think it's already long enough, so what I'm going to do is put stage 3's analysis in the next video. And it's a little bit different than the analysis of these stages, so I guess it deserves its own analysis video anyway. So we'll continue with this next time, and I'll see you guys then.